we're going to look at today is basically two things. We're going to look at functions of two variables and their associated surfaces, and we're also going to learn about partial derivatives. Okay, so two things in this lecture. Some of these things will mean absolutely nothing to you, so don't worry too much about that. Okay, so let's motivate this study. Our world is a very complex place, and when we try to model complicated phenomena, what we tend to do is understand and realise that complicated things depend on many variables. Okay? You can look at the following example. You know, wind power is very trendy at the moment. So the amount of power, P in watts, available to a wind turbine can be summarised by the following equation. So you've got a few constants in there, and you've got two variables. R, the diameter of the turbine blades, and V, the wind speed. So you can see from that relationship that the power depends on two things: the radius of the blades of the turbine and the velocity or the wind speed of air flowing through the blades. Okay, that's a real simple one. Now at school, you would have studied functions of one variable. You would have learnt calculus and, differentiation, integration, and so on. And what we're going to do today is extend this idea to functions of two or more variables. So why would you want to do that? Well, it gives us the power to more accurately model more complicated things. Okay, so functions of one variable are great, but they are limited. They are limited in their scope. Okay, so let's start with a couple of simple examples. So essentially you're going to see functions in this form. Now strictly speaking, f is the function here, okay? But because people are used to seeing, y equals f of x, sometimes we write z equals f of x comma y. So x and y are the two independent variables. And you can say that z's the dependent variable. Z depends on x and y. Okay, so let's have a look at some examples. Here's a function of two variables here, just a polynomial. And a good first question is, well, what would the domain of a function of two variables be like? What would its sort of general setup be? Well, it'll be, in general, a two-dimensional set. Okay, so when I have r squared here, I mean the plane, right? Real numbers. Here's another example of a function of two variables involving trig functions. We can put any x and y into this function and we'll get a well-defined output. So the domain is, again, r squared. If you look at this example, we can't divide by 0, right? So we have to exclude all the points from the domain where x equals y. So as a real simple, diagram, you can think of f as a function machine. And you put two real numbers into f, and the machine goes to work, and it spits out a value, right? Spits out a value, f of x comma y. Okay, that's about as simple as I can make it. You should all have an idea of what a function is. Okay, with functions of two variables, is that better? With functions of two variables, you've just got two inputs. Okay, so we're going to learn how to visualise and sketch the graphs of these more elaborate functions. They're going to be pretty simple, but there's a couple of definitions to look at. Okay, so I'll give you geometric drawings to really explain what these things mean. But just bear with me for a second. Okay, so we talk about level curves of a function. Well, that is just the points or the curve in the plane where a function has a constant value. So essentially you just set your function equal to a constant and draw the graphs in the xy plane. Right? We call that a level curve. The set of all points in space consisting of xy, f of xy, for x and y in the domain of f, is called the graph of f. Now the graph of f is also called the surface, z equals f of x comma y. So let me give you some visual insight into what I mean there. Now in general, the functions that we're going to look at, z equals f of x comma y, the graphs are going to be surfaces. Surfaces, okay? So in this picture, I've drawn in the axes. You can think of this rectangle representing the domain of the function. It might not be a rectangle, it might be something else, like a disk or something. And for each point in the domain, you've got a corresponding height above or below the xy plane, given by f of x comma y, okay? Okay, so we're going to learn a little bit on how to draw these surfaces. Okay, so there's two important principles with sketching surfaces. I guess before we get to that, why do we want to sketch surfaces? Well, if we can sketch surfaces of functions, then it gives us at least a first step of understanding the behaviour of the function. If we know the geometry or the geometric behaviour, well, it gives us a good idea of what the function's doing or the graph's doing. Okay, so I'm going to use two things, contour curves and level curves. They're kind of the same thing. They're just, just a little slight difference between them. Okay, so a contour curve of a given function f is a curve of intersection between a horizontal plane and the surface. Okay, now I'll give you a good picture of what I mean by that in a second. Now, if we sketch our contour curve in the xy plane, then we obtain what is known as a level curve of f. Okay, so let me give you an example of what that means. Some geometry, right? Here we've got a surface that's shaded in green, and we've got a plane that's horizontal. I guess it's parallel to the xy plane. In this case, the plane z equals 75. So you can see in the picture that there's a curve here where the plane and the surface intersect. That is a contour curve. Okay? And then you can see that, well, this curve here and this curve here, basically what we've done is just moved this contour curve down and sketched it in the xy plane. Okay, they're kind of the same curves, but they just lie in different planes. All right? So that smaller circle down there is known as a level curve. A level curve. You might think, well, what does this have to do with sketching surfaces? I don't want to learn about curves, I want to learn about surfaces. Well, I'm glad you asked. Basically, the nature of these contour curves and level curves, they in part determine the surface. Okay? So that's why they're very important to understand. Okay. So here are some crazy surfaces with the associated level curves drawn in. And you can kind of see that, when things get quite steep, the level curves are closer together. And you should be able to kind of see some sort of relationship. It might not be obvious now, but it'll come with a little bit of time. So basically, think of these curves as just being slices with planes parallel to the xy plane and then just pushed into the xy plane and sketched. All right, so here's a couple more. Maybe you don't want to stare at them for too long. But we're going to learn how to produce those things and sketch some simple curves. Now, usually I do not prepare my lecture slides ahead of time. Okay, otherwise you're just sort of presenting material and you're just sort of copying it down. Right? A monkey can do that. However, today we're short of time, okay, because you need to get stuff covered before the first tutorial. But this is a good example of what you might see in a class test. It's not a very involved question, but it's maybe worth 2 marks or something. Here we have a given function. Sketch some contour curves in R3 of this function, and also sketch the corresponding level curves in the xy plane. So, we are going to consider the intersection of the surface with the plane z equals c, where c is a constant here. Okay? And we're just going to pick and choose c to suit our needs. Okay, so essentially, I'm going to consider this z equals f and let z equals c, where c is a constant. So what I'm going to do now is pick a few different values of c and see what happens. Oh no, that was terrible. We'll edit that one out, Josh, okay. All right, so that's terrible. All right, if c equals 1, then basically I just replace 1 here and I try to see what kind of curve that equation represents. Okay, so in this case it's an ellipse. So I know in the plane z equals 1, the contour curve for this f will be an ellipse. Okay, let's put in another one, say c equals 2. If c equals 2, then I just go back to my equation, put in c equals 2, and then I can rearrange this if I really want to and get the standard format for an ellipse. Okay, I haven't done that there because I wanted to save a bit of space. But the point is it's a larger ellipse. All right, so what happens if I chose, say, c equals minus 1 here? Anyone? Anyone? What's that? Oh, interesting. Yeah, we're only working with real valued functions here. Yeah, there's a problem with c if you choose c equals minus 1, let's say. Okay, because this is, something squared is always greater than or equal to 0, right? So if you put a negative number there, you're going to run into problems. So you can't just pick this c to be anything. Okay, what happens if we chose c equals 0? Anyone? 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 Hands? Come on. Yes, be brave. Yes. Yeah, that's right. X and Y will both be 0. So what would our contour curve be? It will just be a point, right? Yeah, just be a point. Good. Okay. So what I've done now, and again I won't do this usually. I will grind these out for you in class. Is I've drawn 2 ellipses. So this one is here, and this one is here. So they are contour curves drawn in R cubed. Now, to get the level curves, all I'm going to do is squish those down and plot them in the xy plane. Okay, again, my drawing's not very good, as you can see, but I've got something good for you on the next slide. Now, of course, Maple can do this really, really well. There's a command in Maple, plot 3D. I've got some appendix at the back of your notes giving you some examples on how to use Maple to produce this. Okay, so if you wanted to, if you put in c equals 0, well, that would be there and there. Okay, so note with each of these curves, I've put in the value of c. So you can see here that these guys, basically this labeling each of these ellipses in the xy plane tells you how far to lift them up above the xy plane or push them down. Okay, so this outer ellipse lies 2 units above the xy plane. All right? Okay, anyone still going? All right, good. All right, so we can use contour curves and level curves, but we can also use vertical planes. Okay, so what we're going to do is look at how the surface intersects with various planes. So here we're asked to sketch the curves of intersection between the surface that we had before and the YZ plane and the XZ plane. Again, this is going to give us geometric insight into how to sketch the surface. Okay, so it's very easy. We just realise that the YZ plane is just the plane x equals 0. So you go up here and you plug in x equals 0 and you look at what kind of curve you get. Okay, you can't get much easier than that. Okay? And for the YZ plane, you're going to let y equals 0 in here and look at the corresponding curve, right? Okay, nothing too difficult with this. We recognise that this is a parabola. And the other equation of intersection will also be a parabola. Okay, so nothing really difficult there. So we've got a couple of things now. We've got contour curves, level curves, and some intersections with the various planes. So what we've got to do is put it all together somehow. All right, so okay. So for the first one, essentially I've let x equals 0, so I'm going to be drawing it in the YZ plane. So basically I just want to draw this parabola. It's going to look something like this. And similarly for part II, I'm going to have a parabola very similar. So basically I'm drawing z equals x squared. Now I've drawn them very similarly, but they are actually different parabolas, you can tell. Okay, they don't really have the same shape. All right, they're parabolas, but a little bit different. Okay, so how do we put all that stuff together? How do we put all that stuff together? Well, if we combine our contour curves with these guys, I'm going to get something like the following. Okay, I'll come back to this if you haven't got it yet. Okay, these are the contour curves, and these are the intersections with various, well, it's one intersection with a particular plane, vertical plane. Okay, so hopefully you can see from that you get a little bit of depth from the picture. Of course, it's hard to draw, you know, sometimes if you haven't done it before. Okay, we call this thing an elliptic paraboloid because the contour curves are ellipses. Okay, and the intersections with various planes are parabolas. Did you get that last one? No, it was you, wasn't it? Did you get it? Is it all right? Okay. All right. So that's a good, that's basically something that you might get on a class test. Sketch this. Well, to do that, it's a good idea to sketch contour curves, level curves, and maybe an intersection with one of the vertical planes. Then put it all together. That's all it is. So, thank you. All right. Now, I have given you an independent learning exercise down the bottom. Basically, I've asked you to sketch the graph of this function. Oh. Now, this is hard. It's hard to draw the contour curves for that. Okay, so what my suggestion is to sketch the level curves first and then lift them up or push them down accordingly. Okay, but if you can do a question like that, you're doing well. Okay, I've left that as an independent learning exercise. All right, so just to give you a little bit more insight into the geometry of this problem, the blue, you have this at the back of your notes in the appendix. Okay, the blue curve here is an intersection with one of the planes, so is that red curve, and the green curve is the contour curve, the ellipse. All right, so you might think, well, why do I need contour curves? I'm studying engineering. I want some applications, man. Well, I'm glad you asked. Contour curves and level curves basically signify physically that if you were walking around a contour curve, you would be walking around at a constant height. Let me give you an example. Okay, this is actually a site, I guess a survey from my parents' house. I'm keeping it personal. And you can see these contour lines. I guess they're level curves in this picture. But if you walked around one of those curves, you would stay at the same height. Okay? So this is like, hopefully you can see the house here and the streets here. This is the front yard. Okay? So this is one good application of contour curves and level curves. Maps, surveying. Let's move on to something that you will be slightly more familiar with, differentiation. Can I have a show of hands? Who's seen partial differentiation before? Has anyone heard of it? Yes? Where have you seen it?
I started tutoring.
Sorry?
Tutoring.
Tutoring, okay. Have you seen it as well? I think your hand went up. Come on, man. No? Okay, all right. Partial differentiation, do you want to sit down, man? Just join us. Join us, it's okay. Otherwise, I'm scared you're going to leave, Partial differentiation is important because if we're going to deal with these functions of two variables, we know that calculus is very handy for modelling, understanding physical problems. What we're going to do in the rest of this lecture is look at partial differentiation. Okay, so, bless you. Let me just give you the basic idea. What we're going to do is propose a method and an idea, a concept, I guess, of determining the rate of change of a function with respect to one of its variables. But we're going to keep the other variable fixed. Okay? Now you might think, well, what does that mean? Well, let me show you. Let me show you. All right. This is the limit definition of a partial derivative of a function with respect to x. Now, you can see here, this function has two variables, x and y. Okay, so there's actually going to be two basic partial derivatives, df dx and df dy. Okay, so this is the kind of notation that we use. You can see it's just the limit of this kind of quotient where we move in one of the variables only and keep the other one the same. Okay? Now, just like regular calculus and when you differentiate at school, you hardly ever use a limit definition, do you? You just sort of, you can do it in your head or, you know the basic ideas and the basics method. It's the same with partial derivatives. Okay? Basically, df dx with the curly d's, that's to signify its partial derivative, is just the derivative of f with respect to x and just imagining y as a constant, imagining y as fixed. So let me give you a geometric interpretation. Now, at school, you learn that the derivative is just a slope of a tangent, right? Tangent line. Now, this more general derivative is just the same, but there's a little twist. Yes, it's the slope of a tangent line, but this red line is a tangent line to a surface that lies in the plane y equals y naught. Okay, so you can see here we've got a point. Okay, we want to calculate the derivative of f at this point. So this, I guess this green plane is just the plane y equals y naught. So we go up, intersect that plane with the surface, and you get a line, that blue line there. Okay, so the blue line is just the curve of intersection between the vertical plane and the surface. Okay, if you intersect that, you get a curve. The derivative is just, in this case, df dx at x naught comma y naught, is just the slope of this line, of this tangent line. Okay, so yeah, it's the slope of a tangent line, but there's this plane that comes into view. All right, just like you have df dx, you can also have df dy. So it's a similar story with the limit, except you're changing the second variable and keeping the first variable fixed. Okay, to calculate df dy, just differentiate normally with respect to y, but keep the x variable fixed. Imagine it's a constant. Okay, so you also have another geometric idea of a tangent. You can see how the plane's going the other way now. This is the plane x equals x naught. All right? Okay, so let's do an example. Okay, this is real simple. Here's a given function of two variables. It's a polynomial, pretty simple. Calculate the two partial derivatives, df dx and df dy. So what do? To calculate df dx, treat y as a constant. So wherever I see y in there, I'm just imagining it's a constant. And I differentiate normally with respect to x. Okay, so let's just work this out. Now, when I write the curly d's there, the d dx, it means I'm going to take the derivative, partial derivative, of what's in the bracket here. Now, just like the regular derivatives that you know, you can either expand this out or do it straight up. So if I imagine y is fixed, well, let's expand it. Okay, so what's this first thing going to be? If y is a constant, what's d dx of this going to be? Who can tell me? 2xy, that's right. Very good. Who said that? Well done. 2xy, because that's just a constant. And if you wanted to be a little bit, careful about it, you could say, oh, I can pull that y out the front. Oh, yeah. What about this second term? I'm imagining y is a constant, and I'm differentiating with respect to x. So it's just going to be 0. That's right. So my partial derivative is another function of two variables, 2xy in this case. It's not always functions of two variables, but in this case it is. Okay, let's have a look at df dy. Okay, and again, I won't pre-prepare these slides probably after the next lecture because, I like to sort of be with you and write it out. Okay, so we go up to f and we treat x as a constant and differentiate normally with respect to y. So let's have a go with that then. Okay, so I'm not going to expand it now. So what's the first term going to go to when I differentiate it? X squared. And what about the second term? 4y cubed. Thank you. Okay, now that's a real basic example, but it just gives you the basic method for how to differentiate these things. Okay. All right, so here's another example. This is one that I prepared earlier. Here, basically, we're just finding derivatives, and those derivatives are general functions. Okay? What happens if I wanted to calculate the derivative at a certain point? Nope. Okay, so here we're asked to find the values of these partial... You guys all right? Yep. Find the partial derivatives at a particular point. So basically, we calculate the two derivatives first and then sub in the point of interest. In this case, the point is x naught equals 4, y naught equals minus 5. Okay, so you just differentiate normally and then at the last step, plug in those numbers. Okay? All right. All right, a couple more examples. Now, one thing that you might be noticing here is that I'm switching the notation. Before I was using curly Ds, now I'm using subscripts, f sub x, f sub y. They all mean the same thing. Okay? Now you need to be on top of all the notation for these derivatives because they might, who knows what's going to be in your class test. So you need to know the curly Ds and you need to know the subscripts because they're used all the time and interchangeably. Okay, so calculate these two values. So if this is our function, what's f sub x going to be? We imagine y as a constant and differentiate normally with respect to x. Who can tell me? What's it going to be? Hands. Yep. Yep, y e to the xy. Well done. So we... So at the point of interest, 1, 1, okay, so for the second question, we're asked to calculate the partial derivative df dy at a certain point. So what's f sub y going to be? Well, imagine x is a constant and differentiate normally with respect to y. So we're going to get y equals... f sub y equals x e to the xy. So we get 2. All right, now they're pretty easy questions, but what you'll find over time is that you'll just automatically differentiate in your head, basically. You know, once you've got the process down pat, it doesn't take that long. All right, so here's a good independent learning exercise. You think you're good? Have a go at this. Here's a function defined by this expression here. I'm challenging you to show that df dx is 0 when x and y are both 0. Try it. If anyone can do it, see me after class. I'll be pretty impressed. All right, so let's have a look at a pseudo application. It's not a real application, but here we're back to our power function. Oops, I guess I should put it down. All right, we're back. Okay, so we're asked to calculate the rate of change in the power with respect to the wind speed at the instant when the radius of the blades is 1/7 and the wind velocity or the wind speed is 1. So what we want to do is calculate dp dv. So if I differentiate this partially with respect to v, remember I'm holding r fixed. I imagine r is a constant. So basically I'm going to differentiate normally with respect to v, so the 3 is going to come to the front, and I'm going to get something like this. Right? But I'm interested in the rate of change at a certain point in time or a certain instant. So I need to sub in these two values. So if I sub in here, I'm going to get something like this. And I can cancel off the 49s, and I'm going to get something like, is it 3 pi on 80? Good. Okay, again, a fairly straightforward example, but we're just really taking baby steps at the moment. This is a V, by the way, not an R. Okay. Okay, so what other rules do we know from differentiation back at school? We know product rule, quotient rule, hopefully we know them, chain rule. I think that's about it. For partial derivatives, all of these things apply. Now we'll look at the chain rule in another lecture, but here's some basic product and quotient rules. Okay, now in all of the above, u and v are the functions, and they both depend on x and y in general. Okay, so you can kind of think of these as the regular product rule, regular quotient rule, just with partial derivatives replaced with the derivatives that you saw at school. Okay, so here's another example that I've created earlier. So here we've got a product, y times sine xy. So it's two functions multiplied together. We've taken the partial derivative with respect to y, df dy, and you can see how hopefully, in this part, we've applied the product rule. Okay? You still assume that, in this case, y is the variable and x, you treat x as a constant. Just differentiate normally with respect to y. Aha. This is a really good example. Okay, here we have got a paraboloid. That's the yellow, the graph is the yellow surface. Now we're asked to calculate the slope of that, the tangent line, to the parabola at the point x equals 1, y equals 2, z equals 5. Now, why do I like this question? This is a good question because it forces you to geometrically think about what you're calculating. Okay, it's not just, oh, I know how to do derivatives, yep, whatever. Okay, can anyone tell me, are we looking for df dy or df dz, df dx or df dy here? Sorry? Are you sure? Why? Why do you say that?
Because it's a tangent.
Yeah?
We basically learned that tangent is dy by dx, not df by dy.
But no, but in this more general setting, that's no longer true. Okay? So it's still a tangent line, but it's a special tangent line in a special plane. Okay? Yes?
The tangent line seems to be running in the y-z plane, so we're going to be looking at that, sure.
In the, yeah. So okay, so what do you know? If we move along the plane, let me go over here. If we move along the plane, y is changing, but x is not. X is just 1, all along that plane. So is it do we want df dy or df dz? Sorry, df dx or df dy? Df dy, right, okay. Df dy. No, we don't want that. Okay, so that's what we're looking for. We're looking for the slope of that particular tangent line. All right, so let's calculate the general derivative, df dy. So what's df dy going to be? to I. So it's going to be 2 times 2. Yeah, we're happy about that. Okay, so that's a good question because it forces you to think about the geometry of the thing you're trying to calculate. Good question. Okay. Now, just with regular calculus, we can do higher derivatives. Remember back at school you could do the second derivative, third derivative, second derivative test? Well, for these functions of 2 or more variables, you can talk about second order partials, third order partials, etc. Now, the important thing here is that there are 4 second order partial derivatives. 4. Okay, so you can see, you've got repetition here, and these 2 in the middle are known as mixed partials. Now, we'll talk about those tomorrow. So see you all then.